All right. All right. So this is the plan for the rest of the semester. We're gonna finish chapter 29 this week. Next week is the Thanksgiving week. No classes. After Thanksgiving, and we come back, I'm gonna give you a review for the final exam. All right, so let's continue to look at the weighted graph algorithms. So this is the part we apply our data structures and object-oriented design and algorithms and into this graph design. The class for the unweighted graph, for the weighted graph, and we have the algorithms and to support the data structure. So you can see this is the way how we solve the problems like this, the graph problems. So we have a lot of data. So the graph has a lot of data, and so you have vertices and edges, and so there changes dynamically. So you can have an empty graph, and you can have many vertices and a lot of edges, a lot of data. So, and all this representing real application. So it depends. You can have, you can see a lot of applications for this. And for this, so you have a data, you can process data. So how do you add more data? How do you remove data? So the vertices, edges, and it can be added and removed dynamically. And also how you're going to process it. And you can do a search, a depth first search, and breadth first search. And you can do for the weighted graph, and you can find the minimum spanning tree and the shortest path. And there are additional algorithms you can add in. So we're not going to cover it, but this is the most basic things and the classic things, and for the graphs, and we cover it in the book. And actually, when you take your next class, algorithm design analysis, and there's a lot of overlaps and with this class. So you're going to see all the data structures we have, the list, stacked queues, priority queues, and binary trees, and aviary trees. And then we have the graph algorithms, and this is actually would be also be covered in the your next required class, the algorithm design and analysis. All right, so now the shortest path algorithm, we have introduced the algorithm for finding shortest path. And this is a very well-known algorithm. And there are actually a couple of algorithms for doing this. So this is the in the literature. So this is the one, it's a very popular one, is Dijkstra's algorithm. So this algorithm, you're gonna find from a single source to all the vertices in the graph, find the shortest path. And just note that this is for the non-negative weights. And that's most of the situations we have the non-negative weights. And so the way, and we approach this, and the intuition is, so we're gonna start from a vertex, we call it a starting vertex, we pick up this, and then we're gonna expand it and expand it. So you expand it, it means we're gonna add a vertex and to the existing shortest path tree. So the result of finding shortest path is to get the shortest path tree and root it at the starting vertex. All right, so initially, and we don't have anything in the shortest path tree, and now we're gonna add the ones with the smallest cost. So we define this as the cost associated with each vertex. The cost is this, and so the cost is actually it's the distance for this vertex and to the source. All right, so this is the cost here. So look at, we define this as the cost associated with each vertex, and cost S, and that's the starting vertex. Of course, it's 0 to itself. The distance is 0. And then all the others now are infinite. So when you choose the smallest one, and that's the smallest one, the one it's starting vertex. So of course, you're going to pick this one. And so that's the first one you're going to put it into the shortest path tree. And then after you add this vertex into the shortest path tree, you're going to adjust all the cost, all the vertices adjacent to the starting vertex, so they can be adjusted now. So there was infinity, and now they're going to change it and to the just initially it's going to be just the width on the adjacent edge, and for each adjacent vertex. So the cost is updated. So this is to keep doing this is the while loop. Each iteration, you're going to find the shortest, the smallest cost, the vertex, and add it into the shortest path tree. So doing this and all the way through, and all the iteration, eventually you're going to bring all the vertices from the original graph and into the shortest path tree. So that's the idea, and we describe it and use this as the algorithm. So here, and you can practice it and using this example and see how you're going to start with the initial, and this is the initial state and the initial graph. So it's like this here. And so this is a T is empty. And here we're going to start this from the vertex 1. And the 1 is, this is the cost is 0. And all the others infinity. All right, so you're going to bring this vertex 1 so into T now. All right, you're going to add this into T. Now all this vertices adjacent to this 1, and their cost now are changed. So the cost for this 3 is 10, and the cost for this 6 is 9, and the cost for this vertex index with index 0 is 8, and the cost for this 2 is 5. All right, so now we're going to pick the smallest one is this vertex 2, and its cost is smallest is 5. All right, so we're going to bring it in. So now look, when we bring this in here, we're going to change the cost for this 0. So 0 here, and was 8. So now you're going to have this 5, 2. It's going to be the smaller one. So this added together 6, right? So now you can see that is going to be this, for this 0 here, the cost is now becoming 6. So it was 8, now it's 6. So the next vertex you're going to pick it up, this is the 0. So this is the shortest. So we're going to pick 0 now. 0 is added, and now you can adjust the cost for this this 5, and now it's going to be 10. It's 4 plus 1 plus 5. So this is the 10. So now you can see this is for the 5, for 5. It's right here. It's 10. All right. So adjustment is made, and now we're going to pick the smallest one. And so now it is this 8 is the one. So 6 here. Okay. So we're going to add 6 now. And so 6 is added, and we make now adjustment on the cost, and now, and look at the smallest one here, both are 10, 10. So please note that the red means the vertex is already added into T, so that's here. So we only look at the ones in black here. It's any, you can pick either 3 or 5, so let's pick 3. So it's like this, and so you make adjustment here on the cost, and so now the next one, you pick the one with the smallest, the 10 is 5, so the 5 is going to be added. So that's how you see this example works. All right, so this is the algorithm, and let's now write the code for this. So let's look at the code. So I think there's a lot of things you can practice here. Is, hey, you think about it. Can I write code myself? Okay, so you can write the code yourself and see how close your code is compared with the code in the book. So that's what help you to improve your coding skills. Okay. All right, so let's now do this here. I'm going to open another tab. So here, I'm going to duplicate this tab. Okay, and now I'm going to okay. All right, so refresh, and now I have this. All right, I think what I'm going to do is to have this 2 tabs side by side. So this is the one here. And now, and this is here. I'm going to reshare the screen, reshare the entire window here. Going to do a reshare. All right, so this is the entire window now. You can see this 2 side by side. All right, so here, this is shortest path. Okay, can you see both now here? Shortest path.
Yes.
So, okay, good, thank you. This is the algorithm right here, shortest path right here. Okay. All right, so we're gonna have this, this is T be a set that contains the vertices whose paths to S are known. Initially, T is empty. So what I'm gonna do is, instead of using the set right here, I'm gonna use a list, because I want to know the sequence, and you're going to add the vertices into the shortest path tree. I want to record that sequence. So which one you pick the first, and next. So I'm not going to use a set here. So I'm going to use it that they want. It's use a list. So here, I'm going to use a list. So you're going to write this list right here. See, the list is here, T. It's right here, T. So we just use a array list. And so you just keep adding to the end. And the cost for this adding a vertex, it's all of one time. It's constant time. All right, so here, the next here is the cost S, we're going to define this array. So this is the array. We're going to define this array, cost array. And this is the array. And here, initialize all the values to infinity. And that's double dot positive underscore infinity. And the cost for the first one, the source, here, source vertex, right here, the source vertex is 0. So that's the one here. It's cost brackets source vertex, and here is 0. Okay. All right. So now, also we need the parent. See, when you have this shortest path tree, it's a tree. So you have this information, the root, the parent. All right. So this is the so we need to have that parent here, and the parent. So this is to define and the array, and here's parent, and the root, the parent of the root has special value -1, indicating this is the root. All right. And now we're going to write this loop, the while loop. So the while loop is right here. While t dot size is less than get size. So that's the number of vertices in the graph. We need to find this u. Find the u. So here's the u. It's let's set this u as not determined. So -1 means this is not determined yet. All right. So the we're gonna find that's the minimum cost. So the current minimum cost, it's infinity. It's a big one. All right. So we're gonna go each of this value, the cost, okay, for each vertex here. So this is for all the vertex, each one. So if this is not in T, all right, so it has to be not in T. We're gonna, the one is already in T, we don't consider it's already there. So not in T. If the cost I is less than the current minimum cost, and we're gonna update that. So the current minimum cost is updated, and also U is updated. So after this for loop, and U is now determined. We find this U and with the minimum cost. So this is here the smallest cost right here. Not in T, and with the smallest cost. Okay. All right. So go back here. All right, this is defensive programming, and we use right here. It's U. If U is not determined, means you cannot find U. It's the graph is not connected. So in that case, we're gonna break it. So we don't really find anything. We have to break it. So break out this while loop here. All right, we cannot continue. So else we're gonna add this U to T, and now this for loop is do the adjustment right here. This for loop and corresponding to the algorithm do the adjustment right here. All right, finally, so you're gonna have the shortest path. So this is new and shortest path tree. So look at the shortest path tree here is this constructed, the source. So here is source, vertex, that's going to be the root. And the cost, it's the one I also need to have this cost, it's useful and for each vertex. So eventually you're going to have this cost, you find that's the one, it's going to be the shortest path from each distance for each vertex to the root. All right, the cost, and so we have this is source. Oh no, the parent first, parent, and then the search order. Search order is T, and the cost. It's right here. Okay, so this is the one. It's the shortest path tree. All right, so this is the you can see this is the from the idea intuition to the algorithm, and then finally we're going to implement it all right here. This here. Okay. All right. next, so what I'm gonna do is to look at the, okay, this one here. I think I'm going to talk about this, the case study on this wedded nine-tail problems next time. So the first I'm going to look at this this one here. It's the programming project. Okay. So the programming project. Okay, so here I'm going to, okay, here. And programming project right here. All right. So there's only one here. This is the one. The description of this exercise from is given right here. Okay, so I'm going to copy and paste. All right, this is the Word file. I'm going to open this Word file now. All right, so this is the Word file. And this is 29. And this is the first one right here. Okay. All right, find a minimum spanning tree. Okay, and write a program that reads a connected graph from the input and displays its minimum spanning tree. The first line in the input contains a number that indicates the number of vertices. And the vertices are labeled as, okay, so n vertices, so starting from 0, and the last one is n-1. The next line describes the edges in the form of U1, and here is V1 and W1 and U2 and V2, W2. So this is the format. Each triplet, so here is separated by the vertical bar, describes an edge and its weight. So edge from U1, V1 there's edge, and the weight is W1. All right, so here, this is the example here. So here's, you can see this is the graph, and 0, 1, and we have this is the weight is 100. All right, so please note that we assume the graph is undirected, means it goes both ways. So from 0 to 1, and there's also 1 to 0, so it goes both ways. If the graph has an edge UV, so there's a 0, 1, and there's also an edge from 1, 0, you have to represent in both directions. So here, look at this input is 6 vertices, and 0, 1, 100. But you don't see here, there's a 1, 0, 100. So in the code, you have to add both edges. You pick one, and then you have to add both. All right. Your program should prompt the user to enter the input, create an instance G of weighted graph, invoke g.print weighted edge to display all edges, invoke get minimum spanning tree to obtain an instance tree of minimum spanning tree, and invoke this tree that get total weight to display the weight of this. Okay, so that's what you do. All right, there's more hint here, and for this, how you do the process here. So this is more for you. You can see how you do this. So what I want you to do is you give it a try and see if you have problems, and you let me know. And if this is a very common, and I'm going to discuss in the class. So, but first, please give it a try and see how you do this. So when you do this, all these things, just be patient. Do it one step at a time. We're writing the code. So the whole thing, the process, all this writing the code is it's just you do it incrementally. So if you look at it in the whole picture, you do first you're going to design it, okay, in the high level, and then you get down and into implementation. And when you do the implementation, and you don't do implementing the whole thing one time, so you implement one part and test it, and then add another part and test it. So this, by doing this, you can narrow the error. So you know, oh, this is because I introduced new code, and the error is due to this, the new code. All right. So please read this more here, everything, and I want you to read it. And there's one thing here, you're going to see this is only at the very end, you're going to see this. You're going to use this to test your code. Use this one right here. So here, use this to test your code. You have to have this and writing this, everything. So this actually gives a lot of help already here. If you go with this one here, so you're gonna see, and this, it has a lot of information already here, the code, and it's already put together for you, so you don't have to copy and paste on your own. So it's already here. So you just write your code right here. Write your code here. Okay. Okay. So I'm going to give you the opportunity to study it on your own, and so we I think I'm going to stop now this class, and so we're going to we have luxury of some time this semester. This semester is very interesting. It's the first time, so we have this 3 lectures every week. So it actually it's more time, because the exam, if you have 2 lectures, your exam is just, you know, 1 lecture. It's already that a week you spend half of the week now just on 1 exam. So now exam you spent only 1/3 of the time on the exam. So I think we saved some time. We have some extra time for this. We're gonna write finish everything by the end of this week, and then we do a review after Thanksgiving. Any questions?
No, sir.
All right. You have a good day, and so we'll see you next time.
And you too.
Okay, bye.
Have a good one.